Alright, let us begin. So, this time, unlike previous solving things, I've already pre-annotated everything, so that should hopefully make um, just getting the information across faster. We have, for the first question, this is a SN1 reaction here. SN1 because it's got only one thing in its slow step, so that's why I've marked here, happens by itself. If you struggle with visualizing all these different compounds, so one bromohexane, one bromo-2-methylpentane, and all that, I highly recommend just writing them out until you find what you're looking for. In this case, we're looking for a tertiary halogenoalkane. Tertiary because this bromine is connected to a carbon that has this, it has this, and it has this. This allows it to form a very stable carbocation, which means that just by itself it's going to start the reaction where the nucleophile comes in and takes its spot. And the other type I have a picture of somewhere further down. So yeah, this one, C. Then draws from info from AS. So this question, number 2, it's kind of interesting in that it does draw information from your AS. So the reaction is between your you have two different iodoalkanes, so those are two halogenoalkanes containing iodine. When they are hydrolyzed, the iodine is freed up in the same way that this bromine is freed up here. It's basically the same reaction, but with a different setup, I guess. So iodine instead of bromine. And when that iodine is freed up, if there's silver nitrate present, then the iodine will combine with the silver nitrate. Oh, wait, he's in the waiting room. Huh. There is. Are you sure? I don't see anyone. Am I blind? Have I forgotten where the. No, it should show up right here, right? Let me see if I can figure that out. Yeah, okay. Um, Adian needs to try again, I think, because he's not he's not showing up on my side. I just tested with a different account of mine, and that does show up, so there we go. Welcome. Yeah, for whatever reason, I didn't get a notification for you the first time, but when you tried again, it did show up.
I think my laptop was lying to me.
Google, small indie company. Hard for them. So the first question here, it's an SN1 reaction. If you have trouble visualizing all these different names, I highly recommend quickly sketching them out, kind of like how I did it here without drawing all of the hydrogens, just to save time. And that way you can spot which one is the tertiary halogenoalkane. Question 2 is combining the same concept as question 1 with information you learned at AS, which is that the silver nitrate will react with the iodine that's given up to form a precipitate. Remember, the colors are white for chlorine, cream for bromine, and yellow for iodine. So the answer here is C, because time to form a precipitate is what we're looking for when that iodine is freed up in the same way that the bromine here is freed up in question 1. Then question number 3, here you have a bunch of graphs, and it these questions are definitely very, very annoying to deal with. Off the bat, you can like discount numbers C and D because there is no version of a concentration time graph that makes those two shapes. If you're tracking the concentration of iodine over time, it'll either remain it'll either be going downwards or it'll either be going downwards in a straight line or it'll be going downwards in a curve. Those are the only two ways that the concentration of iodine could possibly change in a reaction. It's always decreasing because a reaction is happening. You can take out C and D in that way, and then between A and B, you're asked which is correct for the rate of reaction, and you're told here that iodine is not in the rate equation, right? You're given the rate equation. So if iodine is not in the rate equation, then the answer has to be B, where nothing you do with the iodine changes the rate of reaction. So then you have question 4. This one's a bit of a trick question again, I would say, because it's which of these is not a suitable method. And the reason C isn't a suitable method is because your reactants are acids. The concept of quenching and titrating is a method that is used in other contexts. But in this context, it can't be used because you're titrating an acid, right? So there's no point quenching with an acid if you already have an acid. Question number 5, this one is one of those like ln k is equal to whatever, whatever. It follows the y is equal to mx plus c format. So you can see here, I've once again matched everything up to the y is equal to mx plus c format. We know that m stands for the gradient, and that's how you match it up with the rest of it, right? So y is ln k, x is 1 over t. And in this case, in all cases, remember, 1 over t does not take the negative. The negative goes to the gradient. This will cause a little bit of an issue down the line, and I'll point it out where the problem I noticed in the question paper is that there wasn't a space between the division symbol or the fraction symbol line and the negative symbol, so you can't really tell that it's there, so we'll have to make a little bit of a change to some of the answers, but it's a very small change. So the numbers won't change, basically. Alright, question 6. I kind of hate it a little bit. It's not a very nice question. A lot of it hinges on memorizing what the different graph shapes look like. So 6a is asking for which graph is reactant concentration on the x-axis and rate of reaction on the y-axis, right? If it's reactant concentration on the x-axis, that means this is a question about initial rate time graphs. Concentration of on the x-axis means you're measuring initial rate of reaction. Concentration on the y-axis means you're measuring the concentration itself over time, which will always go downwards. So immediately, because it's not concentration on the y-axis, it's concentration on the x-axis, you know that the downward graph cannot be the answer. Initial rate, you will know that there are only like 3 shapes: straight line, like a straight horizontal line, a straight diagonal line, and then a curved line. So first question is, which graph is y rate is first order? First order is straight line. Here, memorizing these shapes will help you a ton. Like, it'll just make you go through these types of questions faster. For B, the answer is C, which graph is for product, concentration, and time. So this time is on the x-axis and concentration is on the y-axis. So the first question was an initial rate time graph. The second question is, again, this thing, a concentration time graph. So our options are either straight down, which is 0 order, or a curve for first or second order. We are told that this is a 0 order, so it's going to be straight down. So that is... Oh, right. There is no straight down for this one, right? So our only option is graph 3. So actually no, that makes sense because it's a zero order reaction, right? So zero order reactions can go straight up. But it's a very strange graph. I don't really like these questions for that reason because it's all memorization. But yeah, x is on the time axis. Time is on the x-axis, meaning you're measuring over one reaction over time. And in a zero-order reaction, you can, I suppose, build a reaction where the concentration of... Oh, it's because it's Y product. Okay, okay. See, again, they threw another spin at this one. So this is this shape over here. You can see the mouse, right? Yes. So it is this shape, but it's going in the opposite direction because concentration time graphs, as they're drawn here, is reactant over time. And this question gave you product over time. So if reactant decreases over time, product increases over time. Isn't it fun? So yeah, concentration time graphs. Another shape to memorize. Number C is even meaner because now it's temperature on the x-axis and rate of reaction on the y-axis. It's meaner in the sense that this has nothing to do really with orders of reaction. Now we've got moved on to temperatures, but yeah, it would make graph 4. Temperature has a quadratic scaling to time. So if you want to help visualize what that experiment would look like, I have some text here. So same reaction with initial rate of reaction on the y-axis. So again, initial rate of reaction is on the y-axis, and you're trying out different temperatures on the x-axis, and that gives you a quadratic graph, a curve going upwards. Then question 7. I think 7's an interesting question. So it may be difficult to visualize the math, so I've drawn this diagram here. What you have here is a reversible reaction, right? And you're told that the reactions delta HR, so this thing, the gray number here, has a value of plus 53. And you are also told that the forward reaction has an activation energy of plus 173, right? So that means that this blue line over here, going from H2 plus I2 all the way to the EA threshold up here, this part is worth plus 173. This is the bit that has the value of 173. And remember, if an arrow goes up, it is always a positive number. If an arrow goes down, it's always a negative number. That's what this bit under the delta HR is saying. So the activation energy to go from H2 plus I2 all the way to EA is 173. Of that, plus 53 of that energy is the lattice energy, so delta HR. Not the lattice energy, the enthalpy of reaction, delta HR. Which means going to EA from the product side, so 2HI, would require plus 173 minus 53. You subtract this gray region out from the blue region, which gives you this green region, and that's why the answer is plus 120. So, as always, if any of these questions don't completely make sense to you right now, mark them with a star, and I can explain it again on the board where I can walk through each of these pictures and explanations and all that. Question 8 is orders of reaction, and we will see some really nasty order of reaction questions. So generally, what you're looking for is finding out multiplied by how much is the change you're trying to track, and then that number to the power of how much is the change in the initial rate. So for example, here in this blue text, I have times 2, and then the initial rate went times 4. Times 4 is 2 to the power of 2. So that's how you can tell that this is a second order change. And then for the other reactant, even though it changed here, there is no change in the order of reaction, so that means it's 0. So that's why it's 0 for Y and 2 for Z. Time for half-life is 10 seconds, so this is just reading off the graph. Your graph starts at 20, so the first half-life has to be at 10, second half-life has to be at 5, and so on. So you were just taking whatever the measurement for the time of reaction in minutes is at 10 seconds, and then if you want to confirm, you can take the time between then to the 5-second mark to see what the next half-life is. But that part is up to you. They just care about the first half-life. Then, this is just some mistakes. I'll erase that later, the blue bit here. Number 10, this is the same as question 1. So again, this is 2-bromo-2-methylpropane. It's exactly the same compound. It is a tertiary halogenoalkane, meaning that the bromine is connected to a carbon that has 3 other carbons attached to it. And as a result, it has a rate with just the halogenoalkane. And that's why whenever you see the rate is K times of R halogenoalkane and nothing else, you know that that's a tertiary halogenoalkane. It's SN1, that thing again. 11 is one of the more chill questions, so it's just rearranging the rate equation, canceling, and getting your number out. So hopefully that's not too bad. And then B, the rate is unchanged when the hydrogen ion concentration is doubled. Again, this is just, reading off the rate information. Like the rate is equal to K times this compound and H plus AQ. They're both to the power of 1. Right, they're both first order reactants, so it's not possible for hydrogen ion concentration to have no effect on the rate. Its hydrogen ion is first order. Then 12 here, again, lots of confusing things to look at. I highly recommend drawing a box around diagram 3 to use as a reference for later questions like this, because this type of question will come up a lot, as it tends to do. What we have here is an SN2 reaction. You can tell it's SN2 because the OH minus is actually doing something to the halogenoalkane, and then they form this intermediate together. Whereas in the previous SN1 examples, this halogenoalkane breaks apart on its own first, and then the nucleophile, this OH minus, can come in and do its own thing. So the fact that both of them are participating tells you that this is SN2, and they already told you that in the question, right? It's which diagram shows the mechanism for a second order reaction, SN2. 13, again, memorizing shapes of rate time and concentration time graphs will help you out here. I'll try to make like one of those like one-page references for that, especially like when they have like the graphs that they don't even include in your book, like product over time instead of reactant over time. I'll try to put together something that's hopefully coherent for that. 14, again, here it's more orders of reaction stuff, but instead of giving you a table to look at, it gave you some words to read. So that will make it a little bit more confusing, but remember, being able to translate the rate equation into a sentence can help a lot. So rate is equal to K times NO to the power of 2 times O means that the slow step requires 2 NOs and it requires 1 O2. And if it requires 2 NOs, that means it's second order, and if it requires 1 O2, it means it's first order, right? So when concentration of nitrogen monoxide doubles, that's the second order one, then the concentration of oxygen quadruples, this one, oxygen is Okay, wait. I made a mistake here. Let me see if I can fix it real quick. This one should be 2 to the power of 1. One here. And that one should be 2 to the power of... Okay, yeah. So the nitrogen monoxide has a power of 2. What is that? The nitrogen monoxide has... Okay, well. Click and drag it. Okay, there. Nitrogen monoxide has a power of 2 because it's second order. And the oxygen has a power of 1 because it's first order, right? In both of these cases, we are putting a 2 down here because it tells us it's doubling, and here it's quadrupling. Quadrupling is... Wait, no, never mind. I was fine earlier. Yeah, okay. This is to the power 2 quadruples, and this is I'm gonna have to put a star next to this one. I'm gonna have to talk through this one on the whiteboard. I think I should have written more information here. Reading off it is much harder to explain than I had initially anticipated, so we'll talk about this one in class. Moving on to B. Same as previous in the sense of same as this one. Same as this. Like, write out the k is equal to whatever, and then you cancel out the numbers, and that's how you get... Or cancel out the symbols, rather, and that's how you get this. Number C, only correct answer is A. This one's also hopefully pretty straightforward. You're just rearranging to make NO the subject. Don't forget the square root. They do try to bamboozle you by giving you an option where they don't do the square root. So that's something to look out for. This one is, once again, SN1. So here it's important to remember the 1 in SN1 is just telling you information about the slow step. What it is not giving you is any information on how many steps there are in total. We know that it has 2 steps because this is a reaction we study. We spend time learning about the number of steps involved in halogenoalkane nucleophilic substitution. We learn that primary will do SN1 and tertiary will do SN2. But just because SN1 and SN2 are the known orders does not mean we know how many total steps there are for every SN1 and every SN2 reaction out there. We only know that it's 2-step for this particular pair. The SN1 of the halogenoalkane, we know, is 2 steps because we learned the steps. Number 16 is another one of those questions where it's kind of semi-memorized. It's annoying. But this time they tell you that the fast step involves 2 of these, the NOs, forming an N2O2. And then the slow step involves that N2O2 reacting with an H2. It should be an H2 here instead of an H, but you get the idea. Reacting with an H2, and that is our slow step, right? Which means for the slow step to work, you need twice the NO, and then H to the power of 1, right? So NO to the power of 2, and H to the power of 1, that combines together to form 3, and that's why the overall order is 3. Now, it's annoying to have to remember it like this because NO shows up in a fast step. But it's important to notice that NO shows up in a fast step that makes the chemical that is required in the slow step. And that's why, even though it's in a fast step, its presence is in the rate of reaction, in the order of reaction. Question number 17. Again, this involves the Arrhenius equation. This is just rearranging, right? So you have M, meaning gradients. That's just like geometry. M is EA to the power of R. That means ea to the power of r is minus of m. Oh, m is equal to minus ea over r. So that means ea over r is equal to minus m, which means ea is minus m times r, which is minus of the gradient times the r. Number 18, this is another one where you rearrange the question. It seems straightforward. You're just rearranging to make k the subject, but they threw in a little bit of a trick or a twist to it, where they gave you a concentration for b, but you can't use that concentration for b in your value of k, because b is 0 order, which means whatever this number is inside this bracket, you take it to the power of 0, it ends up being a 1. So this is what the value of k is actually supposed to be. Rate divided by square of a concentration. Question 19, slow step has one of these, so it shows you, right? Rate is k times of this reactant, CH3COCH3, times H plus. It's first order for the CH3COCH3, and it's first order for H plus, and there is definitely no I2 in the slow reaction at all, because it doesn't show up in the rate equation. From that information alone, you can eliminate everything except A, because A is the only slow step that has no iodine in it. That's basically how they want you to figure this out. The fact that the slow step involves, like, again, this intermediate chemical that you've never seen before, that is less of the thing that you actually use to figure it out than the fact that I2 is not involved in the slow step. I thought this was really funny. Allow suspiciously large subscripts after elements. Whatever they say, you know? The examiner knows best. So if you ever wrote suspiciously large subscripts, you're in the clear. Anyway, question 20. From question 20, we move on to the written questions, so those should go by pretty fast. This is the equation. What you will notice is for this equation, they just gave you all the information, right? There's another question like this that I thought was also quite interesting, so we'll look at that. So this part here, question B1, justifying why you've selected a particular number as the order with respect to that reactant can be pretty hard. I highly recommend writing this down if you need to, and I will give you this as a PDF as well, this like annotated markscheme document, so you can copy it down from there later. But yeah, it's very, very important that you any kind of idea that you find difficult to describe in the answers that you give, you should copy directly from the markscheme and make an effort to memorize the wording that they use. That'll take you very far. These experiments are really, really dumb. No real scientist would ever do their experiment like this, but again, let us take a look. Here we see that the NO, the red markings show us the NO goes from 4x, goes through a 4x change, right? From 0.002 to 0.008. At the same time, the initial rate is having an 8x change. 8x, when taken to the power of 4, is 4 to the power of 2. That means it's second order. At the same time, over here, there is no pair of H2 entries where H2 is the only thing that's changing. In one of them, NO changes in all of them, NO changes at least once, right? So it's like 2x, 2x every time. So what we have to do is we have to combine everything. So here we can see that NO is doubling, right? It's a 2x change. And H2 is also doubling. That's a 2x change again. We already know that NO is second order. That we established already. Which means that this change over here, this one, which is also 8x, this blue change, part of it is being contributed by a 2 to the power of 2. That is coming from the NO. And the rest of it is being contributed by a 2 to the power of 1. So that's the part that has to be coming from the H2, and that's how we can tell that H2 is first order. These questions, and they keep getting more and more ridiculous the further down you get. They are very, very logic intense. They're basically puzzles. I don't see the point of making them so needlessly complicated and convoluted, but it is what it is, and I will include all these annotations for you to look at in your own time. Here, I've pointed out that all of these have TE, which is transfer error, meaning that if you are lost on how to solve these things, you can just write whatever you want and then use those numbers to finish up the remaining questions. So you can, if you don't know what these are, you can just make up an order for them, skip writing the justification, and then use those orders to do calculations, and you will still get these marks at least. Again, this is another place, C1, where articulating this idea might be difficult, so I highly recommend writing it down if you need to. So this one is the possibility of 3 molecules, species, particles of gas colliding in the right orientation is low. Then we have this one, which this, again, seems like a really difficult question. Like, how are you supposed to know what the slow step looks like? But as you can see from all these different options, you can write whatever you want here. You can make up any combination of chemicals, including just smashing all the slow step reagents together, and that's fine. As long as you correctly identify which chemicals are the slow step reagents using what you see in the given information, you're good to go. And then here, the explanation again. Rate equation must include all the species up to and including the rate determining step. Rate determining step, remember, is the slow step. So everything leading up to the slow step is going to be involved in the rate equation. So make sure you write that down as well if you need. Question 21. Here, once again, if you made any mistakes or didn't answer this fully, I've underlined in red the parts that I think are the most important, so write those down if you need them. Question number 2 is another one, give a reason why. It's a 1-mark question, but there's a lot of different options, so again, write down whatever you think you'll need. I will make this available for you to take your time copying stuff. Give a reason why the concentration of sodium hydroxide used was very much greater than the concentration of 2-bromobutane. So all of these are different phrasings on the idea that we don't want the sodium hydroxide to affect rate of reaction. We're trying to make sure that 2-bromobutane is the only thing that is changing in significant ways so that it is having an effect on the rate of reaction. B1, again, it's initial rates, using that to work out the order of reaction. C4H9Br here is going on a 1.5 change. Isn't that lovely? So it changes to a multiplier of 1.5, and we'll see here that the initial rate changes to a multiplier of the same amount, so that means it's to the power of 1, which means this is first order. And then what you'll see here is, again, they've changed 2 numbers at the same time. We already know that C4H9Br is first order, so if it's a 2x, then the initial rate would be doubled. And then this is also 2x'd, the NaOH, and we see that the initial rate altogether is times 4. That means it's 2 to the power 1 into 2 to the power 1, so 2 times 2. That means each of these were first order. The powers are what's telling us what order they are. These powers are taken to the multiplication numbers here in the changes in concentration. A very, very convoluted way to do these types of questions, but it is what it is. Question number 2, calculate the rate constant for the reaction. Use the data from experiment 1. So rate constants, this should be pretty straightforward at this point. It's just rearranging and then substituting the numbers in, and also remember to work out the units. This is SN2. Use the data from experiment 1 to oh wait, no, this is C. This is C. State why the reaction of 2-bromobutane with aqueous sodium hydroxide being second order indicates an SN2 mechanism. Anything that is SN2 is always second order. So, how would you phrase that? By saying that the C4H9Br and the NaOH, or the OH minus, either will work, are both involved in the rate determining step. Again, if you struggle with phrasing, very, very helpful to copy things down directly from the markscheme with the intent of memorizing them. So find a way to mark them so you can keep going back to refresh yourself. Then they ask you to draw the reaction mechanism. Again, this is something where if you're not comfortable drawing reaction mechanisms, you should get really comfortable with it. They gave the skeletal diagram. I've taken the skeletal diagram and made it more like a displayed diagram. You should include the hydrogens. I've skipped them for space, but you should always include the hydrogens as well. So there'd be one hydrogen with this middle carbon and then there's like 3 hydrogens on the edges and all that. The curly arrows are very important, and I've marked them. So number 1 curly arrow is this one, where the carbon-bromine bond breaks, and the arrow goes from the covalent bond line in the middle to the bromine. Number 2 curly arrow is from the lone pair of your nucleophile, your OH minus, to the carbon. This part should be familiar because this is something you need to know for your AS as well, the nucleophilic attack, as it's called. And then the last mark down here is for showing both the transition state, this whole thing up here, and giving it its appropriate charge, which is -1. So the transition state is denoted with the dashed lines to both bromine and the hydroxide, and then this whole thing has 1 extra electron, which gives it a negative charge. Here we have a bunch of math. We love math. This is our first graph. It should be a straight line because, again, remember, when we are plotting ln k against 1 over t, this is a y is equal to mx plus c format. This is a straight line graph. If you struggled with the numbers because they were all like 10 to the power -3, you could because every single number is 10 to the power -3, you can actually take that out and put it on the axis label, which is what I've shown here. So you can do 1.15, 1.20, 1.25, 1.30, and then on your axis label, you write 1 over temperature T to the power of Kelvin, meaning it's Kelvin is the units, and into 10 to the power -3. When you say this, it's written here. If numbers used on x-axis are without the power of 10, allow 10 to the power 3 or 10 to the power -3 on the axis. So once you knock that out, you can put it on the axis, and that's fine. Again, here, it's another rearranging, making the gradient using the gradient equation to work out EA. Here is where that negative symbol might have gone missing in your question paper because they were too close together to the EA thingy. So if your number ended up being a positive number, make it a negative number. It's just the sign that would be wrong if you did this without putting the negative sign there. Otherwise, it's very simple rearrangement, algebra, that sort of stuff. In B, it's important to note that just saying the value is large will not count for any marks. You can see it's very large, but that's not good enough. There are a multitude of ways to answer it, though, so you should copy down any pair of sentences from here that you like best for your answer. So any pair of statements is fine. And then C, explain the trend in the value of the rate constant K as temperature increases. So as T increases, K increases rapidly. These are 3 points. Again, if you missed any of these points, or if you want to improve the phrasing of any of your sentences, I highly recommend copying these down. I will make this available. Then we have another graph. This time it is initial concentration and initial rate. So this is a rate time graph. Straight line, that means it is first order, right? And they tell you as much. So, because it's a straight line, it is first order. That's literally all you need to say to get that justification mark. This is probably the one that made me the maddest. This is an awful setup for an experiment. So let's work through this one at a time. The green number here, first order, this is from the graph, so we can set that aside. We don't need to think about it. The blue number here, we're also going to ignore for a bit. We're going to look at the red number first. So this red number, this bromine, went 3x from experiment 1 to experiment 3. At the same time, initial rate also went 3x, which means 3 to the power 1, which means it's a first order. That's great. Now let's compare experiment 1 and 2 to figure out what the heck is the order of reaction for the hydrogen ions here, the H+. The bromate, BrO3-, goes 5x. It is changing 5 by a multiplier of 5 between this and this. At the same time, the initial rate of reaction changes on a multiplier of 1.25, which is 5 over 4. From this, we know that the 5 to the power of 1 comes from the bromate, which leaves us 1 over 4, which is half squared, which means that the hydrogen is second order. Fun! So, because it's half squared, second order. I'll write down second order here, I forgot. Rate equation, easy stuff. Oh, was that? Okay. All good. Yeah, this is, welcome back, Ryan. This is one of the worst questions in this set. I think this is deeply unfair, but basically, because the initial rate changes at a multiplier of 5 over 4, and this one, which was confirmed first order, is 5x, and this one is half. That's how we work out that this is 5 to the power of 1 because it's first order, into half to the power of 2 because it has to be 5 over 4, not 5 over 2. It is what it is. This number C is a question about heterogeneous catalysts. So again, if you don't remember the theory around heterogeneous catalysts, it's worth writing this down. They basically only ever expect you to just like describe the steps for a heterogeneous catalyst working. Then we have another graph. This time they do give you the graph and you just have to work out the half-lives, which is fairly straightforward. Take the total number here. We have 0.1 divided by 2, which gives us 0.05, which is where the first line is drawn. So 0 to that section there is your first half-life. And then the distance between that section and the next half-life is your second half-life. And these two numbers will be equal to each other. And that's how you show that this is a first-order reaction. Remember, first orders will have equal half-lives. Second order will have unequal half-lives, and there is no like hard and fast way to be sure if something is second order or not. You can only definitively claim if something is first order because the half-lives are constant. If you forget this piece of theory, it's worth writing down and making an effort to memorize it. B1, experiment 2, the initial concentrations. Again, another awful question. The examiners hate you, I'm sorry. Again, we have bromate. It is doubling. And the initial rate also doubles. Doubling for both means initial rate is 2 to the power of 1, which means this is first order. Between experiments 2 and 3, the bromate is going from 0.2 to 0.3, which is a 1.5 times difference. And the initial rate goes on a 6 times difference. At the same time, the hydrogen ion concentration doubles. First of all, we already know 1.5 is first order, so this 6 has to have a 1.5 to the power of 1 involved in it somehow. So what number into 1.5 will give you 6? 4. 4 into 1.5 gives you 6. How is the number 4 related to a 2x multiplier? 2 to the power of 2. That's why we know that this is 2 to the power of 2, second order, and the first part was first order. Very convoluted. Again, rate equation and units, you get transfer error here, so if you don't know your orders of reactions from these awful pieces of data that no self-respecting scientist will ever make, write your own numbers in and then use them for your calculations. Then we have another graph. Again, we have a set of data. This is what the graph will look like. This time, the temperature, once again, is always to the power of -3. The 1 over temperature, that is. And so, once again, you can just skip writing the -3 and put it on the axis label. You're absolutely free to do so. And then from that, you'd work out the gradient. Gradient is always, any 2 points. You draw the triangle, you work out the number here, the difference between the y values, the difference between the x values, divide them, that sort of stuff. Once you have the gradient, you can calculate the, what do you call it? This thing. So, oh, actually, no, I don't want you to calculate EA for this one. This is just all of the marking points here. So you have marks for writing the axis. Do you have to put the axis on the top? I don't think so. Or maybe you do. That's an interesting question. Axis points line must cover. Allow horizontal. Okay, no, you don't. Allow horizontal axis shown at the bottom of the graph. So you can put the horizontal axis on the top of the graph or the bottom. Either is fine. You have to label both axes. These are easy marks, so don't let those slip by. That would be very sad. All points plotted correctly and best fit straight line. That's the usual. Calculation of gradient, sign and units of gradient, usual stuff. Again, remember to work out gradient. It is m, gradient, is equal to minus of activation energy over r, which means, oh yeah, they do want you to calculate activation energy. So that's the last bit here. Once you've worked out the gradient, rearrange to make activation energy the subject, and then work that out. The usual. Alright. That is everything. I have a recording, so you can refer back to this, and I will send you this mark scheme with the little tweaks mentioned. If you have any questions, feel free to ask. Otherwise, I will turn off the meeting at exactly 8.